Hello everyone, we are from Mathematical Method subject group. Today we would like to discuss on the heat conduction through a metal bar. So here goes our discussion.
In this case, consider a thin metal bar of homogeneous material of length L which is placed on x-axis of an xy coordinate system. Thus, the 1D heat equation is given by first derivative of u in terms of t is equals to second derivative of u in terms of x multiplied with k, where k is called the diffusivity of the metal bar. To solve this problem, we assume uxt in this form, where x into x, t into t.
Referring to
These are
Appendix
the
1,
boundary
let us look
condition
at the
for
maple
this problem,
instruction to plot
where
graph for 1C
x0 is equals
for
to
part
0
1 till part
and
4.
xl equals to 0, where
Assign
these are the
fx
homogeneous boundary
equals to
conditions.
x and set a limit
We derive
which is
ODEs
set
for x and
until
t.
5.
Derivative of
Later
u in
find the
terms of
sequence
x, we will get
of 5
x t
for the
prime
integration
and we
part
set
using
as
the
equation
interval
1,
0 to 1.
and second
Then
derivative of
do
u
the
in terms
summation
of
for the
x,
general
we will
formula
get
found
x
in
double prime
1b.
t, and we set this
Plot
equation
a
into
graph
equation 2. And
in
then
2D
substitute equation 1 and 2 into the 1D heat
and also
equation.
plot a graph in 3D.
After
This is
substitute,
how the
we will
graph
get
looks like.
x t prime equals to
Repeat
constant k x double
the
prime
same
t,
thing for the
and then
interval
separate the
0
variables
to
and
2
equal it to a
until
constant.
0 to 4.
In this case, we let lambda is a constant. So then we have two ODE differential equation where t prime equals to lambda kt and x double prime minus kx equals to 0. Now we need to solve both differential equation. Let's look at the first equation, x double prime minus kx equals to 0. To solve this equation, we need to consider three cases for k. We use the boundary conditions to figure out what values of what values of lambda are eigenvalues. For case 1, we let k equals to lambda square more than 0, where lambda more than 0, and we substitute k equals to lambda square into this equation and let it equals to 0. Our x equation is a exponential kx plus b exponential negative kx. We let x0 equals to 0 and substitute into this equation, we will get a equals to negative b. And then we let our xl equation equals to 0 and we substitute L into this equation and we will get a equals to 0 and b equals to 0. Hence, there is no non-trivial solution for case 1. Let's go to case 2 where k equals to lambda square equals to 0. Our x double prime is equals to 0 and then x prime equals to a and let x equals to ax plus c. And when we have x0 equals to 0 and when we solve this equation we will get b equals to 0 and our x equation is ax. For x, when we let xl equals to 0 we will get al equals to 0 and a equals to 0. Hence, there is no non-trivial solution for case 2. Let's go to case 3 where k equals to negative lambda square less than 0. We substitute k equals to negative lambda square in this equation. Our x equation equals to a cos lambda x plus b sin lambda x. We let x0 equals to 0 and when we solve this we will get a equals to 0. And let xl equals to 0 and when we solve this we will get sin lambda l equals to 0 Hence, there is non-trivial solution for case 3. Thus, the corresponding eigenfunctions for this problem are x and x equals to bn sin lambda and x. As we all know, sin theta equals to 0 and we can conclude that lambda equals to n pi. So, sin n pi equals to 0. Now, we have sin n pi equals to 0 and sin lambda L equals to 0. So, by comparing these two equations, we will get sin lambda L equals to sin n pi. Hence, from this equation, we can conclude that lambda L equals to n pi and lambda equals to n pi over L, where n equals to more than 1. Substitute lambda equals to n pi over L into this x and x equation and we will get x and x equals